Ever thought about, what actually happens to your car's bumper in a fender bender? Or like how a trampoline works, how it bounces you back up?
Right. It's all about energy, isn't it? Absorbing it and then releasing it.
Exactly. And that basic idea is what we're diving into today.
These everyday things, they're perfect examples. It's how materials store energy and then give it back.
Yeah.
It's fundamental to, well, everything engineers build.
Bridges, phone cases.
Yeah, all of it.
Okay, let's unpack this then. Today we're getting into energy methods in structural analysis. It's kind of like having a superpower, really.
Yeah, maybe.
Understanding how materials store and release energy lets engineers design, well, almost everything.
And you've given us some great source material on this. Really lays out how forces, moments, translate into stored energy.
So our mission today is to pull out the key stuff for you.
Give you those aha moments. Show you why this topic, which might seem a bit dense, is actually super practical. Full of surprises, too.
Yeah, we want to give you a shortcut, really, to getting your head around this fundamental concept. So where do we start? External work and strain energy.
Sounds good. Let's start with work. External work.
Okay.
In physics, work is force times distance, right?
Yeah.
But here, imagine you're applying a force gradually, like pushing a spring.
Right. You don't apply the full force instantly.
Exactly. The force ramps up. So the work done isn't just the final force P times the final displacement delta. It's the average force.
Which is P over 2.
Right. So the work, UA, is P times delta divided by 2.
And is it similar for twisting something? A moment?
Yep, same idea. Apply a couple moment M, get an angular displacement theta. The work is M times theta divided by 2.
And work is just a magnitude, right? No
Sure,
direction.
a scalar quantity, yeah. That's important. Now, this external work, UA, it doesn't just vanish.
It has to go
This
sit-
gets
oh.
transformed,
Right.
stored inside the material. And that's what we call strain energy, UA.
Ah, the internal work.
Exactly. Caused by the stresses and strains, the internal pushing and pulling as the material deforms. Think of it like winding up a spring inside the material itself.
Okay, and you said it's always positive. Strain energy.
Always. Even if you compress something. Because the stress, say compression, and the strain, the shortening, they're acting in the same direction, mathematically speaking. So their product, which relates to energy, is positive.
Interesting. So it doesn't matter if you stretch or squeeze, you're still storing energy.
You got it. And how much energy gets stored depends on the material.
Right, things like stiffness.
The modulus of elasticity, E, for stretching and compressing, and the modulus of rigidity, G, for twisting or shearing. These properties are key. They tell you how much energy a material can store for a given deformation.
Okay, so we have the basics. External work becomes internal strain energy. Now let's look at different ways you can load something up. Where does the energy actually, hide?
Good question. Let's start with axial load. Simple push or pull along the length.
Like stretching a bar.
Exactly. The formula for strain energy here, UI, is N squared times L divided by 2AE.
Okay, N is the axial force, L is length, A area, E modulus. That N squared seems important.
Very important. It means the energy stored goes up dramatically with the force. Double the force, 4 times the energy.
Wow. And longer length means more energy storage?
Yep. Or, interestingly, if the area A, or the modulus E, decreases, the energy stored also goes up for a given force. Less stiff or thinner stores more energy.
That seems counterintuitive. You'd think stiffer or thicker would store more.
That leads perfectly into that example from the sources, the 2 steel bolts.
Ah, right. Bolt A and bolt B. Bolt A is thicker, mostly, but narrows at the threads. Bolt B is thinner, but uniformly thin.
And you'd think the beefier bolt A would absorb more energy,
Oh,
right?
yeah. Seems logical.
But nope. Bolt B, the uniformly smaller one, absorbs 42% more elastic energy.
42%. Why?
Because its uniformity allows the entire length to deform more evenly. It distributes the stress and strain better. Bolt A has thicker parts that aren't stressed as much, so they don't store as much energy proportionally. The thinner section near the threads takes most of the strain.
So it's about using the whole volume efficiently. Fascinating.
Yeah.
Bigger isn't always better for energy absorption. Okay, what about bending? Like a diving board?
Bending moment, yeah. Here, the energy depends on the internal moment M, which often varies along the beam E and I, the moment of inertia.
Moment of inertia, I. That's about the shape's resistance to bending, right?
Exactly. How the cross-sectional area is distributed. A tall, thin I-beam shape has a high I, resists bending well. For energy, the formula involves integrating m squared over 2EI along the length dx.
So you have to sum up the energy stored in little slices along the beam. Makes sense. The example showed that calculation for different beam types.
Right, like cantilevered beams, beams with different loads.
Okay, next up, transverse shear, like cutting.
Sort of, yeah. A force acting perpendicular to the beam's axis trying to shear it. There's strain energy associated with this. The formula involves a form factor for shear, which depends on the cross-section shape.
But didn't the sources say engineers often kind of ignore it?
They often do, yeah. It's a common simplification, especially for beams that are relatively long and slender.
Why? Isn't that skipping part of the physics?
It is, technically, but the contribution of shear strain energy is usually way smaller than the energy stored due to bending.
How much smaller?
Well, that example showed for a beam where length is 5 times its height, the shear energy is only about 8% of the bending energy.
Ah, okay. So negligible in many practical cases.
Pretty much, unless you have a really short, deep beam, neglecting shear strain energy is usually fine. It saves calculation time. It's an engineering judgment call.
Right. Pragmatic. Okay, last one. Torsion. Twisting.
Bringing out a wet towel or a drive shaft twisting. The strain energy here is T squared times L divided by 2GJ. T is the internal torque, L is length, G is the shear modulus, and J is the polar moment of inertia.
Polar moment of inertia. That's like the rotational version of I. Resistance to twisting.
You got it. And here's that counterintuitive thing again, like with the bolts.
Don't tell me bigger is worse for energy storage.
For a given torque, yes. Increasing the diameter makes the shaft much stiffer against twisting, meaning J increases a lot. Since J is in the denominator, a bigger J means less strain energy stored.
That's really hard to grasp intuitively. We always think bigger diameter means stronger.
It is stronger against breaking. It can handle more torque before yielding or fracturing, but its capacity to store elastic energy before reaching that limit is actually less if it's thicker, because it won't twist as much for a given torque.
Okay, I think I'm getting it. It's about the deformation as much as the force.
Exactly. Energy storage involves both stress and strain.
So all these different types of loading, different formulas, they all feed into this big principle, right? Conservation of energy.
The golden rule, yeah. UE equals a UE. External work done equals internal strain energy stored, assuming slow loading and elastic behavior.
Elastic meaning it springs back.
Springs back completely.
Yeah.
When you remove the load, the stored strain energy, UE2, pushes the structure back to its original shape, doing work back on the surroundings.
So how does UE help us practically, like finding how much a bridge truss moves?
It gives you a really simple way to find displacement, but only under very specific conditions.
Ah, there's always a catch.
Usually. You can use UE directly to find the displacement at the point where a single external force is applied and in the direction of that force.
Okay, one force, one displacement point.
Or one couple moment and the rotation at that point.
Mm.
Super useful for those specific cases, like finding the deflection under a single weight on a beam.
But what if you have, say, 2 weights on the beam? Or you want to know the deflection somewhere else, not right under the weight?
Then UE alone isn't enough. That simple equation has only one unknown displacement, delta, linked to the one known force. If you have multiple loads or want displacement elsewhere, you need more advanced methods. That's its big limitation.
Okay, that makes sense. It's elegant but limited. So up to now, we've been talking about loads applied nice and slowly.
Gradually applied, yeah.
But the world isn't always gentle. What about impacts? Things hitting each other.
Impact loading, yes. That's a whole different ballgame.
Yeah.
Suddenly applied loads, very high forces, very short duration.
Like a hammer hitting a nail or a car crash.
Exactly. Understanding energy absorption is absolutely critical here. To analyze it, we usually make some assumptions.
Okay, what are they?
We often assume the impacting object is rigid, the object being hit responds in a linear elastic way, and crucially, that no energy is lost.
No energy loss, like no heat or sound. That can't be perfectly true.
Definitely not perfectly true in reality. But assuming no energy loss gives us a conservative estimate, meaning the stresses and deflections we calculate are likely higher than what actually happens, which is good from a design safety perspective.
Right.
Better to overestimate the effect than underestimate it.
Right, builds in a safety factor. Okay, so how do we analyze impact using energy?
Think about that classic example. A block falling from a height h onto a spring.
Yeah, I saw that diagram.
The block has potential energy because of its height. As it falls and hits the spring, that potential energy, weight times total distance fallen, gets converted into strain energy stored in the compressed spring.
Okay.
And this leads to a really important insight shown in one of the examples. If you drop that block from just above the spring, So H is basically 0.
Just letting it go from touching the spring.
The maximum compression of the spring, the maximum displacement, will be twice what it would be if you just gently place the block on the spring statically.
Wait, twice? Just from dropping it with no initial height? How?
It seems weird, right? But think about the energy balance. Even dropping from H0, the weight still does work as the spring compresses. That work equals the stored strain energy. When you solve that equation, the dynamic displacement comes out as double the static displacement.
That's a big deal. So dynamic loads are much more severe.
Much more. This leads to the concept of the impact factor, M.
The magnifier you mentioned.
Exactly. It's the ratio of the maximum dynamic force, or stress, or displacement, to the equivalent static value. For that H0 drop case, N is 2. If dropped from higher, N is even larger.
So you calculate the static effect, multiply by N, and get the dynamic effect.
Essentially, yes. Sigma max equals N times sigma static. Delta max equals N times delta static. It's a way to handle these dynamic situations using static analysis plus this factor.
And this applies to kinetic energy, too. Like if something sliding hits the spring.
Yep, same principle. Kinetic energy, 12 milli-G2, gets converted into strain energy. The impact factor concept still applies. That beam example, where a weight is dropped onto it, shows how you calculate the max bending, stress, and deflection using these energy conservation and impact factor ideas.
Okay, so impact is serious business, and the energy approach helps quantify it. But going back to static loads, we hit that limitation with UE for multiple loads.
Right, which is why engineers needed more powerful tools.
Enter the advanced methods, virtual work.
Exactly. The principle of virtual work, developed by John Bernoulli way back. It's really clever. It uses an imaginary or virtual load.
Virtual, like not really there.
Not really there in the actual problem, no. To find a displacement, you imagine applying a tiny force, a unit force, like 1 pound or 1 newton, at the point and in the direction you're interested in.
Okay, an imaginary probe force.
Or, if you want a slope or rotation, you apply a virtual unit couple moment. Now, this virtual load does external virtual work as the structure undergoes its real deformation from the actual loads.
So the virtual force rides along with the real displacement.
Precisely. The external virtual work is just 1 times delta, the real displacement you want, or 1 times theta, the real slope, and this external virtual work must equal the internal virtual work.
And where does that come from?
That comes from the internal virtual forces caused by your imaginary unit load, multiplied by the real internal deformations, stretching, shortening, bending, caused by the actual loads. You integrate this product throughout the structure.
Wow, okay, so it connects the imaginary load to the real deformation indirectly through energy principles.
You've got it. It sounds complex, but it's incredibly versatile. Great for finding truss joint displacements, even factoring in things like temperature changes,
Right.
or if a member was built slightly too long or short.
Temperature changes, how?
Because temperature causes real deformation, expansion, contraction, and your virtual internal forces can do work over that deformation. Same for fabrication errors.
Clever. And for beams?
Equally good for finding displacement and slope at any point due to complex loading. Again, we often neglect the virtual work due to shear, focusing on bending, because it's usually dominant. The example showed applications to both trusses and beams.
Okay, so virtual work is one advanced tool. What about Castigliano's theorem? Sounds fancy.
It is rather elegant. Developed by Alberto Castigliano, it approaches it using calculus, specifically partial derivative.
Calculus.
Don't worry, the idea is graspable.
Yeah.
Castigliano's theorem states that the displacement at a point in a specific direction is equal to the first partial derivative of the total strain energy in the structure, taken with respect to a force acting at that point and in that direction.
Derivative of energy with respect to force gives displacement.
Yes. And similarly, the slope or rotation at a point is the partial derivative of the total strain energy with respect to a couple moment applied at that point.
How does that relate to virtual work? It sounds different.
It's actually fundamentally very similar. Think of it this way. Instead of applying a unit virtual load, Castigliano's method involves including a variable force, P, or moment M, in your strain energy calculation at the point of interest. Then you take the derivative with respect to that P, or M, and then you substitute the actual value of P, or M, which might even be 0 if there wasn't a real load there initially. The maths works out to give the same result as virtual work.
So 2 different paths to the same answer.
Pretty much. Castigliano's theorem is also seen as a statement about the structure's compatibility requirements, how the parts must fit together geometrically. The examples in the sources show it applied to trusses and beams, mirroring the virtual work examples.
Okay, so we've really covered a lot of ground.
We have. from the basics of work and energy.
To how energy hides in different loading types, like axial, bending, torsion, even shear, though we sometimes ignore it.
Right. Then the big jump to impact loading, that surprising factor of 2, and the impact factor n.
And finally, these powerful tools, virtual work and Castigliano's theorem, that let engineers calculate deflections and slopes even in complex situations.
It's a journey from simple concepts to quite sophisticated analysis techniques, all built on that core idea of energy.
And why does this matter to you, our listener? Well, it's not just for engineers designing bridges.
No, these principles are everywhere. Safer cars need to absorb impact energy effectively. Efficient aircraft structures minimize unnecessary weight while handling loads. Even understanding why your phone case protects your phone involves energy absorption.
It moves us beyond just asking, is it strong enough, to how does it deform? How does it handle energy, which is crucial for performance and safety.
Absolutely.
So here's a final thought to leave you with. Thinking about that impact factor. That idea that just dropping something, even from zero height, can double the stress compared to setting it down gently.
That factor of 2.
How might that change how you look at everyday impacts? Dropping your keys, a hailstorm on a roof, maybe even things like sports collisions.
Or think bigger. What does it imply for designing things meant to withstand sudden loads? Protective gear for athletes, crash barriers on highways,
Yeah.
buildings in earthquake zones.
It's not just about being strong, is it? It's about how effectively something can absorb and dissipate that sudden burst of energy without failing. Something to mull over.